Hello everybody and welcome to the chi-square lecture. So today there are actually three parts to this lecture. I'm going to try to see if you like it a little bit better when it is in smaller pieces. The first one is going to be math. That's what we're going to be covering now. The second is on statistical significance. The third is going to be an example worked through PowerPoint. There will also be a couple examples that you can see that I work through by hand, but I want to make sure to give you one in PowerPoint so you can actually read what I'm doing. So with this lecture, we are only going to be talking about what chi-square is and how to calculate it. So thus far, we have looked at continuous data. And you might not fully know what that means, but you'll hopefully understand in a second. And we've done that by looking at means. So we could look at a variable like happiness. We could get these values, add them up, and divide by how many there are, and we could get the average. So continuous variables are any that can go from high to low. It can be basically any number. However, we cannot do this when we look at categorical variables. So these are variables whose values are meaningless. So for example, if you had a list of people's favorite teams, you got in this case 4 people together, you ask what their favorite baseball teams were, you have 3 Yankees, 1 Red Sox, and you can't get a mean from that, right? You could give them values and say Yankees are equal to 1 and Red Sox are equal to 2, but even then you couldn't get an average from them because those numbers are meaningless. So when we're looking at categorical data, we can't use means. We can't look at standard deviations. We can't do things like that. So what do? Well, we look at frequency tables. So if we have our favorite team list here, we could make a table of frequencies. That we have 3 people who say that the Yankees are their favorite and 1 who says the Red Sox are. Now, that's fine when we have one variable, but what about when we have more than one? Well, in that case, we will look at contingency tables. So if you have more than one categorical variable, you can create contingency tables. So in this scenario, we have a researcher who wants to see if cats can be taught to dance. And they take 200 of them and train them with either a reward of food or affection. And at the end of this training, they counted the number of cats who could dance and those that could not. And they got this table. So when you have a situation like this, you have 2 different variables, can they dance and what their training was, you can create a contingency table. You can do this with basically any kind of categorical data where you have 2 variables or more that are related to one another in this way. Now, when we are looking at contingency tables, though, we can also add up all of the values. So we can see not just that 28 had food as a reward and 48 had affection, but we can see the total number that ended up being able to dance. So 28 plus 48 is 76. The number of cats that could not dance, 10 who had food as a reward, 114 that had affection as a reward, 124 total. So a contingency table, is actually a table that has these total columns in them. And this is important for what we're going to be doing going forward. So when you have 2 variables like these, you'll make your table, you'll want to make the totals, total column and row. So what does this have to do with chi-square test? Well, we're going to be looking at Pearson's chi-square test. And if we want to see if there is a relationship between these 2 variables, this is how we do it. So we could see, is there some difference in the result of cats being able to dance based on their training? That is a relatively reasonable question to ask in this case. Because right now, we can see that we have 28 who were given food that could dance and 10 that were given food that couldn't. And it's kind of an opposite situation where most of them given affection could not dance, whereas fewer of them could. And we can also see, though, that we have this variable where food was given to the far fewer, only 38 compared to affection. So what is the relationship between these two variables? Well, we use Pearson's chi-square to do this. All right, so let's rewind a little bit to our first model talk, where we said that in general, deviation is where you look at the sum of all of your observed values minus your modeled values. This is what a deviation score is. So we've seen deviation being your observed values minus the means and squaring them. If we took this a step further, it could be variance if you divide by n minus 1, or if you then square rooted variance, you could get standard deviation. But in general, the way to look at deviation is to see what you have compared to your model and how off it is. So our model in this case, a chi-squared model, as you can see by this, and this is the Greek lowercase for chi, that is going to be equal to, similar to what we had before, but it's observed minus the model squared divided by the model. We don't need to get into why that is. You just go with it for now. And remember, you're going to get these equations on the exam, so you will see what the chi-square one is as long as you know that's chi-squared. So let's get a little bit more specific here. I didn't want to scare you off the bat, but this really isn't that bad. So our model is going to be looking at the observed values for each I and j, which is each row and each column, minus the model for each row and column over the model for each row and column combination. So again, when you have subscripts, that means for that subscript. So observed for I, where I is each row, and j, where it's each column. So what we're going to be looking at is basically each cell in your contingency table. So we're going to be analyzing to see whether each cell is deviating to a certain degree. So let's go to our model more basically. In our case, we are going to be looking at the sum of our observed values minus our expected values squared over our expected values. So this is how we go from talking about models to specifics. So because we can't use means, we have to use frequencies as our base statistic. Remember at the beginning of this lecture, we said you can't use means when you have categorical variables. So instead, we will be using frequencies, simply how often they are there. So our model is going to have observed frequencies and expected frequencies. Now, what are expected frequencies? Because we've already seen the observed frequencies. How many cats can dance after giving food, or being given food, excuse me. How many cats can dance after being given affection, and then how many can't with both of those situations also. Well, expected is how many we would expect by chance alone. So it's what we see versus what could happen by chance. So if we had an experiment with 400 people, we would expect, if it was purely chance, that on average, you'd get about 100 in each category, right? If we had 4 categories and 400 people, if it was purely random, there would be about 100 in each of them. However, we do not have an equal number of cats in our columns or rows. So our expected is not just going to be our total number divided by however many cells there are. Instead, we have 162 that got affection, 38 that got food, and ended up with 76 that could dance and 124 that couldn't. So we have to calculate our expected frequencies. So these are our observed frequencies, how many we actually see. So all of the O's in the equation you already have. Right? So almost half of the equation is already done for you. So what is an expected frequency? Giving you another formula that might look scary, but it's really not. All it means is that for each expected frequency, so the expected frequency for each cell is going to be the row total times the column total divided by the total number of observations in your experiment. So in this case, for the first one, let's say the model, we are looking for the expected for, well, I is our row, so our row could be yes, and j could be our columns, so it could be food, so it would be the expected for yes and food. That would just be the row total for yes times the column total for food divided by n, our total number, which is down here, 200. So now let's just work each of them out. So if our model, our expected value for yes and food, we wanted to do, we would do the row total for yes, which is 76 times 38, the column total, like we talked about, and then divide that by 200. And you would end up with 14.44. So what that means is that by chance alone, you would expect 14.44 to be the number of cats in this cell. But there's 28, so you can see that there's a difference there already. And then we'll do that for each of our possibilities, all 4 of the cells in here. So if we're going to model no and food, so no and food, this value of 10, or the observed value of 10, you do the row total for no, which is 124, times the column total for food, which is 38, and divide by 200, which is 23.56. So you would expect 23.56 cats to be here, but you only have 10. For this cell, it is yes and affection. Well, we do the row total for yes times the column total for affection. So yes is 76 times 162 divided by 200 is 61.56. So you would expect there to be 61.56. It's only 48. And then finally, no and affection would be the row total for no, 124, times the column total for affection, which is 162. Divide that by n, which is 200, and you get 100.44. Okay, so Pearson's chi-square, I just want to point this out again. We've already seen this idea of observed minus expected over something, and you square that. We did that with variance, right? You added up all of the x minus x bars and squared them, divided by n minus 1. This is conceptually similar in what we're doing. It's not exactly, of course, but it's a similar idea at least. This should be kind of, when you see equations like these, they should be kind of setting off a little bit of lights. And you say, I've seen something like that before. You should be more comfortable seeing this going forward. All right. So we now have everything we need, even though you might not realize it yet. We have our observed frequencies for each of the cells. So for yes and food is 28, for example. And we've calculated the model for each of them. So in the case of 2 slides ago, we saw that we would expect this cell, the food and yes cell, to be 14.4 if it were just chance alone. So we have all of our observed values and all of our expected values. Now we just do what the equation says to do. We will take the observed value for one of our 4 possibilities. In this case, it's going to be the I would be yes and the J would be food. 28. We're going to subtract 14.4. Then we square it. And then we divide it by our expected again, 14.4. Then we do the same thing with our next possibility, our next cell. The observed for no and food was 10 minus the expected value, 23.56. Then you divide that by the expected, 23.56. And you do that for all 4 of them. Then you will add those values up. So, again, our chi-square value is going to be equal to the expected minus the observed, 28 minus 14.4 squared, divided by the expected, 14.4. Then we add that to the observed for our known food minus the expected for known food over the expected for known food. We have that here. Do the same for yes and affection, and the same for no and affection. That's what our chi-square is. And we just do the math. We just go from there. This part, yes, a little bit annoying, but that's how it goes. And in the end, after you have to do what's in the parentheses first, then you have to square it, then you do the division, then you add each of those together. You will end up with a chi-square value. All right, I know this is a little bit complicated, so I wanted to stop here and give you a chance to kind of regroup based on what you need. So, again, we're not done with chi-square yet. Where are you going now? Well, it really depends on how you're feeling. If so far everything I've said makes complete sense, then awesome. Then go on to part 2, which is statistical significance. If it makes less sense, you could rewatch this to get conceptually where it's at. Or you could watch one of the examples if math is more the problem. So if you really don't even understand why we're doing chi-square, you might want to rewatch this video. If it's really the math that is messing with you, watch one of the examples. That would be part 3. If you want to see a PowerPoint, or if you want to see me do one by hand, then you can find that. Regardless of how you're feeling right now, I want you to make sure to watch both part 1 and part 2. Part 3 is just an example. If you feel good with it, don't necessarily need to watch it. But wherever you are now, you have to watch part 1, which I guess you just have, and part 2 on statistical significance, because both of those will be on the exam. All right, and I suppose the last option is if you are just completely stumped, then bring some questions to class.